Good morning, and today we are going to be talking about death by space rock. Basically, all the ways that the solar system is trying to kill you by hurling giant rocks at your head. But before we get into that, I'm going to talk about shooting stars, because let's face it, they're a very pretty version of something hitting our atmosphere. So, what are shooting stars? It's dust hitting the Earth's atmosphere. And space is literally filled with these tiny bits of debris. So you got natural debris like rocks and dust and things like that. And then you also have man-made debris like bits of broken satellite, trash from space missions, other things floating around in space that cause problems. But that's another talk all in itself. So most of what hits our atmosphere makes sand look big. Visible meteors are about the size of playground sand, and bigger objects, like gravel-sized, can actually blow up as fireballs. And these sometimes even are big enough that they make the news. So what causes meteor showers? And the short answer to that one is comets. As a comet approaches the sun, the heat causes that comet to heat up, and certain materials like dry ice, frozen CO2, becomes gas, and any material trapped in that ice becomes dust. And then the solar wind, basically all the photons and protons that are emitted by the sun, pushes that out away from the sun. And then this may encounter the Earth, causing meteorites. So comets usually have 2, sometimes even 3 tails. And these tails always point away from the sun because, unlike on Earth, where the tails always essentially go backwards because of air resistance, here it's that solar wind, the stuff that's coming from the sun, that pushes it outwards. And the reason why you have multiple tails is because charged particles react differently to other charged particles and magnetic fields. So you have the neutral part of the tail going off one direction, and the charged portion going off in a different one. So, meteor showers. If the Earth crosses one of these tails, lots of dust hits the atmosphere. And we name the meteor showers after the constellation that the meteors appear to radiate from. For instance, the Orionid meteor shower radiates from the constellation Orion, and it happens in mid-October, and we see 1 to 2 a minute, and this is us passing through the tail of Halley's Comet. So why do they glow? No, it's not friction. Usually friction is the one that's reason that's given, but that's not exactly correct. And they don't burn up either, because these are fundamentally rocks, and rocks don't burn. What happens is, as they're coming in, there's a whole bunch of gas that gets compressed right on that leading edge of the rock. And you might remember from chemistry class that pressure times volume equals the amount of gas that you have times some constant times the temperature. So if you're compressing all of that gas, raising that pressure, lowering the volume, that temperature is going to skyrocket. And that's what causes these meteorites to glow, and also, coincidentally, a diesel engine to work. So, and black body radiation means it glows red. That basically, hey, hot stuff glows red because it's emitting a bunch of light, and we see that as red light. So, this is the same thing that happens when a spacecraft is going through re-entry. So here's a picture of the Orion spacecraft from NASA, and you can see how you've got this glow, and that you need a nice heat shield to protect your astronauts and spacecraft against. So the meteorites will eventually burn up because the heat will cause the objects to melt and eventually evaporate in our atmosphere. So, wasn't this talk about the danger of space rocks? Yeah, so the fact that we travel through comets' tails and get these meteor showers mean that we exist in the same place as some of these comets, just at different times. Now, if we happen to be at the same place at the same time, it's going to be a bad day. So, let's go back in time. So February 15th, 2013. And this was before I became a physicist, but I was still known as the science geek at work. And I had a bunch of coworkers that were afraid of this. So asteroid 2012 DA14, which sounds like an astronomer named it after their license plate, was making a very close approach to Earth. And that license plate kind of name is a code for when it was discovered. So it was the 14th asteroid that was discovered in a given week of 2012. And I believe DA is late July. So it was discovered only less than a year before, and it was 30 meters in diameter, meaning that if it were to hit us, it could destroy a small city. And it passed 17,200 miles from Earth, which is inside the radius of our communication satellites. Now, all the astronomers were very interested in this because we knew that it was going to miss us. We knew exactly where it was going to be, but we wanted to get as good of measurements of its orbit as possible so then we could track it further out and see if it was going to hit us in the future. Now, my coworkers were afraid, and this near miss is a boring way to start this conversation. So let's talk at 9:20 local time on the same day while we were all looking at that other asteroid. An asteroid hit and exploded above Chelyabinsk, Russia. And it was about 13 to 14,000 tons, about 20 meters in diameter, and it hit the atmosphere traveling at 20 kilometers a second. So that's 20,000 meters a second. So 40,000 miles an hour, or 52 times the speed of sound. And it exploded about 20 to 30 times more powerful than the Hiroshima explosion. So at the end of World War II, the U.S. bombed Hiroshima and Nagasaki, which were two Japanese cities, and utterly leveled them, killing 100,000 people, give or take. And that gives us a benchmark. That tragedy gives us a benchmark for the destructive power for large explosions. So that's the unit that I'm going to be using to express the explosive power and the destructive power of these asteroids. So this is a near miss. So the asteroid blew up 30 kilometers, or about 18 miles, above the Earth's surface. And the shockwave blew out windows and caved in roofs for a radius of a few tens of miles around the explosion. And most of the injuries that were caused were shattered window glass. So you can imagine that you're in Russia, you just finished your breakfast, and there's a huge bright light outside of your window. And you go out to the window and you look out going, what on earth is going on? And that's when the shockwave gets you. So that shockwave hits the window, blows all of that glass into your face, and it's now become a very bad way to start your morning. So the explosion was about 30 times brighter than the sun. And it caused blindness in some of the victims, and others were even sunburnt because that explosion was so bright. It contained enough energy that you ended up having faces that were sunburnt from the explosion. Remarkably, there were no fatalities. And a lot of this is because it's Russia, it's Siberia, it's wintertime. And so everybody's wearing heavy sweaters, parkas, things like that. So when they go to the window and that window comes into their face, they're wearing enough layers that the glass doesn't hit any critical arteries. So why was this so dangerous? We had zero warning. We were looking at this other asteroid. We knew all about it, but the Chelyabinsk meteor, we had zero idea that it even existed. And the reason why is 20 meters is a very small space rock, so it's also very difficult to spot. And it wasn't very reflective. And the scientific term for this one is low albedo. It's not shiny. And it came at us directly from the sun. So you can imagine that, hey, look, if we got something small, we're going to need a very powerful telescope a very big telescope, a very expensive telescope to spot that thing. Very big, very powerful, very expensive telescopes should not be pointed at the sun, because then you're going to cause everything involved in that very big, very powerful, very expensive telescope to melt. And that's not the world's best idea. So why were we safe? It hit us at a very shallow angle, and this means that the Earth's atmosphere slowed it down before it could actually hit the surface. And it was made out of rock and ice, which shattered during re-entry. And it was small, only about 20 meters. So it blew up over sparsely inhabited Siberia. Yeah, it was a city, but it's a small city in the middle of nowhere. So it didn't cause as much damage as it otherwise could have. And most importantly, it didn't hit us during the height of the Cold War. Because I can imagine that if this hit during like the early 80s or the late 70s at the height of the Cold War, then somebody might have seen this explosion, gone, oh my goodness, the Yankees are attacking us, and then hit the red button, and all of us are now dead in a nuclear wasteland. Let's keep Fallout as a fictional video game. So what is a near-Earth object anyways? Well, it's basically an asteroid that gets uncomfortably close to Earth's orbit. And most of these come from the asteroid belt when the orbits are shifted a little bit by Jupiter's gravitational field. And most are rocky or icy, but a small minority are made out of metal, mostly nickel and iron. So let's talk about the asteroid belt. And the one thing to keep in mind is that this is home to countless planets, from little grains of dust to the dwarf planet Ceres. But this isn't Han Solo's asteroid belt.
The possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
So thank you, C-3PO. So the odds of actually hitting something in our own asteroid belt is about 1 in a billion. And NASA actually does the math to see if one of their spacecraft going out to the outer solar system is going to encounter one of these objects. Not because they're afraid of it going smack, but because if they're going to get close, they want to be able to take pictures and get some secondary science and calibrate some of their machines on the way out. And to give you an idea of just how much stuff there out there, lots and lots of objects, but they're all small. And if you were to add up all of it, including that dwarf planet, you're still only about 4% the mass of our moon. So let's kick things up a notch. And this is the part of the talk where I try to scare you. So let's talk Tunguska. No, not an alien spacecraft exploding. The Tunguska event was likely very similar to Chelyabinsk, only a lot bigger. Like 1,000 times the power of the Hiroshima bomb, or about the size of the largest fusion bomb that the US ever detonated. So it knocked down 8 million trees over an 830 square mile area. And to give you an idea of how much devastation, this picture taken by the Soviet Academy of Science in 1927, so that's 19 years later, and you can still see that massive devastation that this explosion caused. So it was picked up around the world. So it was the explosion, which was above ground in the atmosphere, read like a 5 on a Richter scale. And given the time that's passed, it's tough to figure out what exactly was the object that hit us, but it may have been a large, somewhere in the neighborhood of 190 meter chunk of the comet Encke. So what it's made of matters. So this is a picture of the Barringer crater, which I have been lucky enough to go visit. And this crater is almost a mile wide and 550 feet deep. And given that this hit about 50,000 years ago, and therefore erosion has happened, it used to be a lot bigger. So this was caused by an asteroid that was way smaller, like a fourth of the across. So only about 50 meters across. But it left this big hole in the ground because it was made out of nickel and iron and therefore survived its atmospheric reentry. So because it then survived all the way to get to the ground, we have a very nice crater sitting in the earth as evidence of this event. So, and this is one of the problems that we've got, is understanding how often Earth gets hit by catastrophic asteroids is difficult. For a crater to appear, it first has to strike the land, and a lot blow up in the atmosphere. 2/3 of the planet is ocean, and ice age glaciers would also hide a crater. If something hits the glacier, it just makes a crater in the ice, and if it hits the land and then the glacier comes over the top, that is now going to be erased. And craters can erode very, very quickly. So a couple years ago, there was a meteorite hit in, I believe it was Venezuela. And all of the scientists that study this went, oh, excellent, let's go take a look. And so they bought plane tickets, and by the time that they had gotten there, it had filled up with water, breached the edge, and completely eroded away over the course of a few days. So yeah, these can get completely erased quite quickly. So a prime example of this is the Chicxulub crater. Now, when I was a baby dinosaur nut, let's face it, I haven't grown up since then. There was a whole bunch of talk about what destroyed the dinosaurs, and this idea that it was some sort of object hitting us was around during those 80s. But the naysayers were like, okay, so if it was a comet, show me a crater. It just doesn't exist. And all we had to do was look a little bit harder for it. So Chicxulub crater is off the edge of the Yucatan Peninsula, and it just completely eroded away. So the only way that you were able to find this is by looking for oil in the area and looking for the disturbance in the bedrock. And they were able to find that using magnetic detection equipment. So this was over 1 billion times, billion with a B, times more powerful than the Hiroshima bomb. It was an asteroid about 6 miles in diameter. And one of the greatest quotes, and I unfortunately can't find where it's from, but I think it's a Scientific American article, said that it sent rocks, debris, and dinosaurs into orbit and beyond. So this is a really, really big thing. And this isn't even the biggest crater that we've found. We've actually found at least 2 others that are bigger. One is in northern Canada, but it's also way, way older, so it's very difficult to see. So how do we know what we know? So NASA has been able to track about 2 decades worth of airbursts, a little bit more now. And what we found is that there's way more than were previously estimated. And we can look at the craters of the moon and compare statistics, because if something strikes the moon, it's going to stay there. And so here's a picture of all of those explosions in the asteroid field. So you can see that over Russia, you got 2 really big ones. The one that's in the middle of Russia, up by Kazakhstan, is the Chelyabinsk. You can also see one over the Kamchatka Peninsula, which is also a very, very large size. But I mean, looking at this, there are a bunch of these that are just happening over water or other spots that are sparsely populated and just weren't spotted before we had the ability to detect them. So what's the danger? This is the part where I'm going to talk about the danger posed by all of these asteroids of different sizes. So let's talk about city killers. So these are about 50 meters in diameter, and they occur once every 500 years. We really don't know the statistics on that yet. But if one were to hit, Tucson would be toast and DC would be destroyed. In fact, the area of destruction would be about the exact same size as that DC Beltway. Let's move up bigger. Metropolitan murderers. So these are 150 meters across. And this would destroy Chicago and all of the suburbs. So it is going to be destroying not just a city, but a mega city. So all of the suburbs, all of the areas, something like Tokyo, which is a very, very large city would be completely wiped off the map. And this would also throw the world climate off of balance. Think nuclear winter kind of a thing. It's going to throw up enough dust that it's going to block enough sunlight that crops and things like that are going to fail worldwide. And an ocean impact isn't going to save us either, because if one were to hit the ocean, it would cause tsunamis on par with the Japanese Fukushima incident or the Indonesian Christmas Day disasters. It's still going to be a really bad day. And these occur once every 15,000 years. But again, we just don't know how often those are going to occur yet. We're working on figuring that out still. So now let's go bigger. Now we're in serious trouble. The state slayers. So these are about 1 kilometer in diameter. So something this big would be enough to vaporize the entire state of Illinois or Florida or anything else of similar size. So an ocean impact here will cause tsunamis that destroy almost all of the world's coastlines, some of them several times over, as that giant wave goes around the earth, rebounds, reflects, comes back, and it's going to be a really, really bad day. So this is going to cause a global climate catastrophe and could even spell the end of the human race, because it's going to be that much of a disruption. It won't destroy all life on Earth, just the delicate kind, like us. And this may happen every 400,000 to 1 million years. So it's going to be a rare event, but they still exist. And so the good news is we think we're pretty good at finding these. So to date, we found 902, and we can calculate where they're going to be, and none of them are going to hit us. Whew. So how do we keep ourselves safe? This is the part of the talk where I try to make sure that you can still sleep tonight. So finding near-Earth asteroids, and finding these are going to be the important bit. And NASA has a whole bunch of robotic telescopes that scan the solar system looking for these objects. There's Linear, there's Catalina, there's Pan-STARRS, there's NEOWISE, there's LSST. There's a bunch of these that look out, get pictures of the sky, and just happen to also be really good at finding these asteroids. And we have found a bunch. So you can see right above my picture that the 902 big ones are all cut out. And even the small ones, we're getting fairly decent at finding. There's still going to be a lot more out there that are small that we just haven't found yet. But we're working at it. And early detection is going to allow us to protect ourselves. So we found these 1,400 plus potentially hazardous asteroids, and the way that NASA defines a potentially hazardous asteroid is one that's 140 meters in diameter. Now, those are still the metropolitan merger, so we're still talking big rocks that can cause lots of destruction on a definitely local, perhaps global scale. And the orbits for all of these have been tracked 100 years out. And the good news is that none of them are going to hit us. This means that you're going to die of something else before the asteroid gets you. Hopefully, that'll be extreme old age, because we're tracked that far out. So here's a map, and this is one of those where when dealing with the solar system, scale is tough, because of course this looks like a full map, and it is. But we're talking about tiny objects that only exist one spot on that orbit. So it's just a really neat visualization of all of those orbits that are crossing Earth's orbit. So all of these are potentially dangerous, but as long as we keep good track of them, we'll be fine. So the Planetary Defense Coordination Office. This is NASA's agency that's tasked with potentially finding these potentially hazardous asteroids and determining methods to deflect an asteroid that's on a collision course. So this is Lindley Johnson. He's the Planetary Defense Officer, and he's the guy whose job I really want. Just to be able to say, I'm the Planetary Defense Officer would just be something really cool to have on your business cards. So he's the one that is in charge of coordinating how NASA is going to keep us safe from all these asteroids. So once we have detected something, how do we deflect it? What do we do? So there is a movie. It is called Armageddon. And it gives an example of all the things not to do. Whatever you do, do not nuke an asteroid. This only works in science fiction. And the reason why is a real life asteroid would break up, causing lots of big collisions instead of one big, huge one. And that's going to, rather than one area of the globe is destroyed, now it's the entire globe is destroyed. And now it's radioactive debris in our atmosphere. Really bad idea. In fact, Armageddon is so bad scientifically that it's used as essentially a hazing ritual at some scientific offices. It's like, okay, watch this, write down all the things that they got wrong. And one of them was that, hey, if you try blowing up an asteroid that big, it's just going to gravitationally recompress, and you have now done absolutely nothing other than make it more dangerous and radioactive. So a prime example of one of these things blowing up, separating out, is Shoemaker-Levy 9. So when I was a baby astronaut, like 1994, I believe, this smacked into the backside of Jupiter. And so here's a picture of that comet that got too close, got broken apart, and then hit into Jupiter, leaving these essentially bruises as it went around. So when you consider just how big Jupiter is, these are bruises on the face of Jupiter, many times the size of Earth. So breaking apart an asteroid just makes it a lot more deadly. But we have other tools at our disposal. We could smack it really hard, and we have experience at doing this. So this is an animation of Temple 1, which was to see, or rather, this is Deep Impact, and it was to see what the asteroid Temple 1 was made out of. So we collided something into it and took pictures of that collision, and it was about equivalent to 5 tons of dynamite. So not big, but it exists. And this was enough to change the velocity 0.0001 millimeters per second. So not much, but it gives us an opportunity to study and see what's going on. And it changed its orbit by about 10 meters. Not enough to keep us safe, but we could imagine scaling this up, maybe. But there's other better options, and boring works better. So we could land a rocket on the asteroid, and we have experience doing this too. So the Rosetta mission with the Philae lander landed on the comet Gerasimov that it was floating out there, and you could imagine putting Sergei Gerasimov, something like that. You could imagine putting rockets on that in order to gently nudge it out of the way. So we could also park a gravity tug near it. So you could put a large, massive satellite next to one of these, and that mutual gravitational attraction is going to pull the satellite that we park towards the asteroid, and thanks to Newton's third law, that asteroid closer to the satellite. Well, you can just move the satellite with the thrusters on the satellite and then just tug it gently out of the way, and this gives you a very efficient way of adjusting the orbit of this asteroid. Only problem is it's slow, but as long as you have early detection, that doesn't matter, and you can tug it out of the way over the course of a couple years. Let's see. The other thing is we could just paint it. And painting an asteroid affects how much of that light gets reflected. And this is just a neat thing, is taking a look at how the asteroid interacts with the sun's light is one of those things that causes large error bars on our knowledge of where this is going to be. we can take that uncertainty and just engineer it for our own purposes and go, hey, look, if it's white, it's going to get pushed out further, and that's going to cause it to miss. And we don't need to miss by very much. Space is big, Earth is small. Missing by a little bit is enough to keep us safe. So this, the Yarkovsky force is that force that pushes it based off of those emitted infrared photons, and it's kind of neat if you feel like looking it up later. And this can redirect that asteroid. So the future, and yes, there still is one. So early detection is the key. So with that in mind, the sooner we find these asteroids, the better off we are, because then we can develop a way to deflect it. And we're getting pretty good at finding them. But if you remember the beginning, Chelyabinsk wasn't detected before it hit. So the B612 Foundation is trying to build Sentinel. Problem is that they've sort of run out of money. But they've done a lot of technological development in order to try to build this. Essentially, it's an infrared telescope that you put in Venus's orbit, and then it can look out away from the sun in infrared, so it's going to be finding those asteroids that's very difficult for us to see from Earth. There's also the possibility of asteroid mining. Remember how at the top of this talk, I was talking about, hey, look, there's most of them are rock, but some of them are made of nickel and iron, and gold, iridium, silver, osmium, palladium, platinum, rubidium, rhodium, ruthenium, and tungsten. So all of those are very, very valuable, and we could conceivably mine those. And these are also going to be valuable for building spacecraft if we want to become a multiplanetary species. And those materials are things like iron and cobalt, manganese, molybdenum, nickel, aluminum, and titanium. So they are particularly valuable for us if we can capture them and mine them. So there's a couple of things to watch if you want more information on this one. So there's 3 novas: Meteor Strike, which is about the Chelyabinsk asteroid. There's asteroid Doomsday or Payday, which is a good one on mining these asteroids. There's also the Day the Dinosaurs Died, which is about that collision that, well, killed all the dinosaurs. And then there's also Astronomy Cast, which is a wonderful, wonderful podcast that I highly recommend. And then there's, of course, the NASA JPL site that talks about near-Earth objects. I just wanted to end on a reassuring note, and that is that nobody in all of recorded history has ever been killed by one of these near-Earth objects. In fact, only one person in all of recorded history has even been hit by one, and that happened in Illinois, and you can go visit that meteorite at the Field Museum.